Alright, let's talk about 3.6 zeros of polynomial functions. So far, we've studied the process of finding zeros of polynomial functions through factoring and formulas. Yet, there are still polynomials we cannot find real zeros for, despite our expansive toolkit of techniques. In this document, we will review and cover a few topics which we will explore further on in more breadth. For now, we will simply state the individual theorems. Let's talk about the first theorem now. It's called the Remainder Theorem. It says, let k be a real number. If a polynomial, f of x, is divided by x minus k, then the remainder is the value f of k. So if our f of x was, say, 3x squared plus 2x minus 1, and we were going to take f of x, so we were going to take 3x squared plus 2x minus 1, and then divide it by, say, x minus 2, then our remainder, r of x, it's saying is just f of what we divided by, 2. So, f of 2. That is, you just plug 2 into this and solve, and it's the remainder. And then you can verify that with synthetic division if you want to. Neat, I guess. Cool. Now, the second thing says the factor theorem. Let k be a real number. Then k is a zero of the polynomial f of x if and only if x minus k is a factor of f of x. Of course. If you have a zero of a polynomial, you can write it as part of the factor. That is, we know that if we get x equals 3 and x equals 2 as the two factors, as the two zeros, then x minus 3 and x minus 2 are the factors. Of course we knew that. Because of this minus, that, by the way, is why you have to change the signs on these. Or why you have to change the signs when you go this way, whichever way you want to look at it. So the remainder theorem and the factor theorem we've been using since Algebra 2. We're aware of that. Here's the rational zero theorem. If the polynomial f of x equals, and then it's just a polynomial, if it has integer coefficients, that is, the numbers in front of each of your x sub whatevers, your x sup whatevers, your power terms, if these are all just integers, -2, -60, 1, 7, 0, but not 1/3, if they are integer coefficients, then every rational zero of f of x has the form p over q, where p is a factor of the constant term a0, that is the last term in here, and q is a factor of the leading coefficient a sub n. And when it's talking about factors, guys, what it's talking about is like the factors of 8. 8 can be written as 4 times 2, and 4 can be broke down into 2 times 2. Okay? This is the fundamental theorem of arithmetic, by the way, that says that we can do this. So your factors are 2 and, well, that's it. Those are your factors. So 2 and then 1 and 8. So 1, 2, I guess 4 and 8 would be all your factors there. So it says that every rational zero is going to have this form. Every rational zero is going to look like plus or minus to each of these, plus or minus, plus or minus, plus or minus, plus or minus, either plus or minus 8 over plus or minus 1, plus or minus 8 over plus or minus 2, plus or minus 8 over plus or minus 4, or the other way, 1 over 8, 1 over 4, 1 over 2, plus or minus. It'll be one of those guaranteed. This thing is incredibly useful. And again, when we get to it, when we need it in the future in calculus, we're going to go over this again real quick. It's super easy then and it's super easy now. But for now, not really worth spending a ton of time on. So we're going to go look at the last two theorems. Theorem 4, the fundamental theorem of algebra. If f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. Moreover, for a not equal to 0, f has exactly n linear factors, with each of the factors being complex numbers. Therefore, f has exactly n complex 0, allowing multiplicities, of course. So, that's it. That's the fundamental theorem of algebra. It was stated a little bit easier for you guys. This is the fundamental theorem's most formal statement. It's what lets you factor things. Neat. Last thing, the complex conjugate theorem. If f is a polynomial function with real coefficients, a complex 0 a plus bi, then a minus bi is also a 0 of f. That is, if it has a plus bi as one of the zeros, then you're guaranteed to have a minus bi as a zero as well. These things are part of what's called roots of unity, and we'll get to this in trigonometry when we get to De Moivre's theorem and we start playing around with that. But for now, that's all that you need to know about that. And that's all you need to know from this entire section. There's not really a lot to get out. Now we can play around with Descartes' rule of signs and do some stuff with the rational zero theorem and play around with that and play around with polynomials some more. But I have found in my personal experience and in my professional experience that it's largely irrelevant to anything that you're going to do right up until you need it. And it's much better to go over it and make sure that you understand it then. So I've went over this so that you've seen it before. But other than that, that's all that there is to it. So you guys take care, and I'll see you in 3-7.